Hello, in this video we'll talk about how to determine the molar mass and density of a gas using concepts related to the ideal gas law. This is contained in section 13.7 in your book. Okay, so the molar mass of a gas is just like the molar mass of everything else. It's the grams of that sample divided by the number of moles. And so if you're ever tasked with finding the molar mass of a gas, given the mass of it and then pressure, volume, and temperature, then you can use the ideal gas law to determine moles, and then grams over moles gives you molar mass. Not really a complicated process, just one that I wanted to point out. And so here we have an example of doing this. Let me scoot this up. So if you have some gaseous allotrope of sulfur, sulfur can exist as a number of different allotropes or formed of just the element. And so we don't know which one it is here, although we do know that it occupies 7.23 liters at 1.05 atmospheres and 750 Celsius. And then you're given the mass of this. So then what's the allotrope of sulfur? Well, we have the mass. Now we need to find the number of moles if we're going to identify this by its molar mass. So, all right, here's moles. You rearrange the ideal gas law to solve for moles. Then we put pressure on the top, volume on the top, the gas constant on the bottom, and then the temperature in Celsius plus 273.15 to get us into Kelvin. So then our units all cancel here. We have the right form of the gas law. That's good. You solve this out, you get some number of moles. Well, if we take grams over moles, that gives us molar mass. And we have the ability to do that. Here's grams on the top, and then moles on the bottom. And this gives us 64.1 grams per mole. Great. So now that we have the molar mass, we can look at this relative to sulfur and say, hey, each sulfur is 32 grams per mole. This allotrope is 64. That tells us that this has to be diatomic sulfur in our sample. And so this is just a contextual problem to give you an idea of how to do calculations relating to molar mass with the ideal gas law. The other thing we can talk about here is density of a gas. So density of a gas, again, is just like density of other things. It's the mass over the volume of that gas. And this one's a little more complicated to figure out how to deal with this with respect to the ideal gas law. So then here I have the ideal gas law written, PV equals nRT. Now let's multiply the right side by mass divided by mass. You could just cancel the masses back out again and get back to the ideal gas law, but we're trying to get somewhere with this. So all right, first step, multiply by mass over mass. Now we can rearrange, and what we're doing in the rearrange is we're multiplying both sides by mass, which has the effect of taking this mass and moving it up over here. And then we're dividing both sides by volume, which takes this volume and puts it down here. And then we're going to take nRT and divide both sides by nRT, which takes the nRT underneath. And holy cow, that got messy, right? But you do those things, and then you can get this format right here. And so it's just a rearrange, and feel free to try it yourself. It's a good algebra exercise to be able to do these kind of things. Okay, but now we're looking at this. We rearrange this on purpose so that we have mass over volume. And hey, mass over volume is density. That's great. On the left side, we have mass over moles. And, well, this is just like saying grams per moles. So if you take the things I outlined in red here and just rephrase it as molar mass, which is this kind of squiggly M here. Now we have molar mass times pressure divided by RT equals density, because again, mass over volume gives you density. So this is a useful equation if you're dealing with density of gases, and I give you this equation on the info sheet of the exams in case you need it. And ultimately it's just an equation, and you can plug various things into it and solve for various other components in it, just like everything else. One further thing you can do with this is rearrange to solve for molar mass. So you divide both sides by pressure, multiply both sides by RT, and that's another way to solve for molar mass. And then you can break the density out into mass over volume if you would like, mass of your particular sample divided by volume of that sample. Perfect. So now we have some new equations in our toolbox. let's see what we can do with them. All right, let's calculate the density of carbon dioxide at this pressure and this temperature. Okay, so here's the formula we're going to use. Density equals molar mass times pressure divided by ideal gas constant times temperature. So first we got to find the molar mass. So carbon 2 times oxygen, there's the molar mass, perfect. Now we're also going to need the pressure in units of atmospheres if we want to use the ideal gas constant that has atmospheres in it, which is the one I typically use. So convert that to atmospheres. And then you're going to need the temperature in Kelvin, because this is a gas law problem. Always put the temperature into Kelvin. All right, now we can just plug these things in. Here's our formula. Here's the molar mass. And then I wrote grams per mole as grams times mole to the -1. Honestly, because I thought to do it, and I want to remind you that these are the same thing. Okay. And then here's the pressure. Here's the gas law constant. And then here's the temperature. All right, now we got to make sure the units all seem to cancel out. So the moles cancel out because on the top, moles to the -1 is the same thing as saying 1 over moles. And then on the bottom, you have moles in the denominator of the units of the ideal gas law constant. So you basically have 1 over moles divided by 1 over moles. That cancels out. Brilliant. All right, the atmospheres cancel, the kelvins cancel, so we're left with just grams over liters, which is good because that's the unit of density we typically use for a gas. For a liquid, we use grams over milliliters, but since gases are so much less dense, we tend to use grams over liters for a gas, and it makes more sense to do so because the numbers come out to be more reasonable. All right, so you calculate this through, you get 1.48 grams per liter. And so that's an example of how you use the density formula relating to an ideal gas to do some sort of problem with density. So again, you can solve for any one of these variables in this equation if you know the other ones, just like every other equation ever. So just be aware of it if we ask you to do something like this. All right, and that's what we have for this video. Thanks for watching.